Every time a lab announces more qubits or a new quantum chip, timelines fill with predictions that Bitcoin's cryptography will be shattered overnight and coins will be stolen en masse. What matters is not just more qubits, but a cryptographically relevant quantum computer. A large, fault-tolerant machine with enough reliable logical qubits and low error runtime to actually run deep cryptanalytic algorithms against real-world keys, and that class of machine does not exist yet. He then unpacks the difference between physical and logical qubits. Marketing announcements often count raw, noisy hardware qubits that error out quickly, while breaking Bitcoin demands thousands of stable logical qubits stitched together through error correction. Public roadmaps from major players talk about reaching the hundreds, not the thousands, of logical qubits needed for a direct threat to something like Bitcoin's signatures, which is why the report calls a 5-year Q-day for Bitcoin, unbacked by current evidence, and even a 10-year window aggressive. Once the panic is cooled, the narrative shifts to clearing up a conceptual error that drives a lot of alarmism, treating all cryptography as if it were just encryption. Blockchain Vane draws a bright line between encryption, which hides information, and digital signatures, which prove authenticity and control of funds. This sets up the explanation of Harvest Now, Decrypt Later, HNDL, attacks. An adversary can copy encrypted traffic or stored ciphertext today, government communications, medical records, corporate secrets, and stash it. If a powerful quantum computer shows up in a few decades, they can try to decrypt this historical data. That is why browsers like Chrome and infrastructures like Cloudflare are already rolling out hybrid post-quantum encryption, combining classical and quantum-resistant schemes to protect long-lived secrets. But signatures don't work that way. There is no hidden message inside a signature waiting to be decrypted later. The risk is that once a CRQC exists, attackers might be able to forge new signatures or derive private keys from exposed public keys going forward. This distinction lets him take some of the apocalyptic edge off the conversation. Old blockchain transactions do not suddenly become invalid or revealed because there was never any secret payload in them to begin with. The danger is about who can authorize future spends, not about reading hidden data from the past. With this foundation, Blockchain Vane tackles the popular phrase, "Quantum will decrypt Bitcoin," and calls it the wrong mental model. A public blockchain is already a transparent ledger. Anyone can read it today without a quantum computer. The nightmare scenario is not some secret diary being unlocked, but a world where a quantum-enabled attacker can imitate owners, forge signatures, derive keys, and spend coins that are not theirs. He stresses that most public chains are actually not vulnerable to HNDL-type attacks, because they aren't hiding confidential data on-chain. The big exception is privacy-focused protocols that really do rely on encryption to conceal transaction contents. If those encrypted payloads are embedded on-chain, they can be harvested now and potentially decrypted later, undermining any promise of forever privacy. For those systems, the report argues, post-quantum encryption and careful design are more urgent than for transparent ledgers. The story then zooms in on Bitcoin and becomes more about social and technical inertia than raw math. Any meaningful move to post-quantum security would require not just a code change, but a coordinated migration by wallets, exchanges, miners, node operators, and ordinary users. In a quantum-aware future, coins whose public keys are already visible on-chain become the first targets. Early output types, reused addresses, and script formats that expose the public key from day one. Even regular spends create a temporary window. When you broadcast a transaction, your public key is revealed and sits in the mempool waiting for confirmation. A sufficiently powerful quantum attacker could, in theory, race you by deriving the private key and broadcasting a conflicting transaction. In the early quantum era, this would likely be expensive and focused on large visible balances, but it illustrates why Bitcoin needs a plan. He also surfaces the governance headache of abandoned or lost key coins. There are huge amounts of BTC that haven't moved in years and likely never will because keys are gone or owners are dead. A migration to new quantum-safe addresses cannot move those coins for their owners. That raises hard questions. Leave them forever vulnerable to any party with a CRQC, freeze them, or even treat them as destroyed. Each choice carries economic and political trade-offs, and because Bitcoin's block space is scarce, even a well-agreed migration would be slow and fee-sensitive. From there, the narrative moves into the engineering trenches. Switching to post-quantum signature schemes sounds like a straightforward upgrade. Swap out one algorithm and you're done, but the report, as recounts it, insists the reality is more complex. Most post-quantum schemes come with much larger keys and signatures, which make individual transactions heavier. He walks through the cascade. Bigger transactions mean higher fees, more bandwidth, more storage, slower node syncing, and more pressure on small operators. That pressure can quietly push networks toward larger, more centralized infrastructure, undermining decentralization in the name of quantum safety. On top of that, some post-quantum signature designs that once looked solid have already been broken in the lab, and many don't support the elegant aggregation tricks used today, like compressing thousands of validator signatures into a single proof. A rushed switch that picks the wrong scheme or implements it sloppily could cause catastrophic failures long before any quantum machine appears. Because signatures are literally everywhere in crypto, every transaction, validator message, multi-sig approval, any design mistake propagates throughout the system. The report's view, echoed in the video, is that developers should start planning migration paths now, but resist the urge to bolt on a quantum-safe label quickly, just to calm markets. In the closing stretch, the video turns from diagnosis to prescriptions. Blockchain. Vane summarizes 7 broad recommendations from the A16Z report. Deploy hybrid encryption wherever long-term secrecy matters. Use hybrid, hash-based signatures in update pipelines so urgent future patches can be shipped safely. Begin designing how blockchains will introduce and support new signature types, and treat privacy chains as higher priority for encryption upgrades. Equally important, the report advises prioritizing implementation security over speculative quantum defenses in the near term. Ordinary bugs, misconfigurations, and poorly understood new schemes are much more likely to wreck systems in the next decade than a surprise, fully capable CRQC. It also calls for sustained investment in quantum research and talent as a national security issue, since whoever gets a cryptographically relevant machine first would endanger not just crypto wallets, but the entire apparatus of today's public key infrastructure. Finally, it urges everyone to keep perspective. There will be plenty of quantum breakthrough headlines, but a stream of incremental milestones does not mean the finish line is around the corner. Blockchain. Vane closes on a note that is sober but not fatalistic. He quotes the report's author as refusing to say a CRQC in 5 years is literally impossible, just highly unlikely, and stresses that the key fact for holders is that developers, companies, and governments are already working on solutions. Incentives across the ecosystem are aligned toward a quantum-resistant future, and progress will arrive in manageable steps rather than as a sudden overnight collapse of cryptography. In that telling, Bitcoin and other major cryptocurrencies are not living on borrowed time so much as they are standing at the start of a long technical transition, one that requires planning and discipline, but still leaves room for these systems to adapt and survive in a quantum world.